allotropy or allotropism, meaning other, and tau rho omicron pi omicron sigma, meaning manner. Form is the property of some chemical elements to exist in two or more different forms, in the same physical state, known as allotropes of these elements. Allotropes are different structural modifications of an element. The atoms of the element are bonded together in a different manner. For example, the allotropes of carbon include diamond, graphite, graphene, and fullerenes. The term allotropy is used for elements only, not for compounds. The more general term, used for any crystalline material, is polymorphism. Allotropy refers only to different forms of an element within the same phase. These different states are not, themselves, considered to be examples of allotropy. For some elements, allotropes have different molecular formulae which can persist in different phases. For example, two allotropes of oxygen can both exist in the solid, liquid and gaseous states. Conversely, some elements do not maintain distinct allotropes in different phases. For example, phosphorus has numerous solid allotropes, which all revert to the same P4 form when melted to the liquid state. History. The concept of allotropy was originally proposed in 1841 by the Swedish scientist Baron Jöns Jacob Berzelius. The term is derived from the Greek alpha lambda lambda omicron tau rho omicron pi alpha. After the acceptance of Avogadro's hypothesis in 1860, it was understood that elements could exist as polyatomic molecules, and the two allotropes of oxygen were recognized as O2 and O3. In the early 20th century, it was recognized that other cases such as carbon were due to differences in crystal structure. By 1912, Oswald noted that the allotropy of elements is just a special case of the phenomenon of polymorphism known for compounds, and proposed that the terms allotrope and allotropy be abandoned and replaced by polymorph and polymorphism. Although many other chemists have repeated this advice, IUPAC and most chemistry texts still favor the usage of allotrope and allotropy for elements only. Differences in properties of an element's allotropes. Allotropes are different structural forms of the same element and can exhibit quite different physical properties and chemical behaviors. The change between allotropic forms is triggered by the same forces that affect other structures, i.e., pressure, light, and temperature. Therefore, the stability of the particular allotropes depends on particular conditions. For instance, iron changes from a body-centered cubic structure to a face-centered cubic structure above 906 degrees Celsius, and tin undergoes a modification known as tin pest from a metallic form to a semiconductor form below 13.2 degrees Celsius. As an example of allotropes having different chemical behavior, ozone is a much stronger oxidizing agent than dioxygen. List of allotropes. Typically, elements capable of variable coordination number and/or oxidation states tend to exhibit greater numbers of allotropic forms. Another contributing factor is the ability of an element to catenate. Examples of allotropes include non-metals, metalloids. Metals among the metallic elements that occur in nature in significant quantities. Almost half are allotropic at ambient pressure. Li, B, Na, California, T, Mn, Fe, Co, Senior, Y, Zr, Sn, La, C, Pr, Nd, Edm, Gd, Tb, Dy, Yb, Hf, Tl, Th, Par and U. Some phase transitions between allotropic forms of technologically relevant metals are those of T at 882 degrees Celsius, Fe at 912 degrees Celsius and 1394 degrees Celsius, Co at 422 degrees Celsius, Zr at 863 degrees Celsius, Sn at 13 degrees Celsius and U at 668 degrees Celsius and 776 degrees Celsius. Lanthanides and actinides, cerium, samarium, dysprosium and ytterbium have 3 allotropes. Praseodymium, neodymium, gadolinium and terbium have 2 allotropes. Plutonium has 6 distinct solid allotropes under normal pressures. Their densities vary within a ratio of some 4:3, which vastly complicates all kinds of work with the metal. A seventh plutonium allotrope exists at very high pressures. The transuranium metals Np, Am, and Cm are also allotropic. Promethium, americium, berkelium and californium have 3 allotropes each.